Everybody, it's Tyler here checking out the Texas Championship, checking in team number 1600, Valor, who has been absolutely on fire this year. Their robot is so slick. I absolutely love it. Of course, we'll be going through that full cargo journey, talking about both hardware and software. They got some new drive modules that you're using this year. I know you're very excited to talk about that as well and talk more about this robot. I have Cooper, Andrew, and Alejandro, and we're going to be talking about everything that goes in this robot coming up here on Behind the Bumpers. Your destination for first content, updates, and gaming.
Welcome to the fun.
First Updates Now is supported by Kettering University. Did you know that over 30% of the student population at Kettering University was in high school robotics? These same students have received a portion of over $7 million in robotics scholarships from Kettering University. See why so many in first chose to go to Kettering University at kettering.edu. If you are planning on attending the World Championship, come meet others in the Fun and FRC Discord community with our combined meetup on Friday, April 22nd at 11 a.m. local. Location will be announced closer to the event, and you can stay updated by following in either the Fun or FRC Discord. Andrew, we're going to talk about the actually the drive mechanisms first, right, that you have. So talk to me about what it is, because I know a lot in the FRC community have not seen this yet. So talk to me on what how you've used it on the robot, what's your experience been with it so far, and just what's gone into it.
So this is our first year using swerve drive, as you can see. These are the swerve drive specialties Mark IV L4 ratios. So it's wicked fast. It's actually called too fast. So it's been extremely useful this year, navigating around people, navigating around defense spots, as well as just lining up for every shot perfectly. That's like with the L4 ratio, we're so fast, we have to keep the robot light, as well as small and simple. And that's something we've really tried to work on in every aspect of the robot. Ball path, shooter, climber, everything is light and simple, which is great for our reliability, which you'll see in our matches.
You know, I know you said this is your first year doing swerve, right? So like coming in and using those for the first time, were there any like unexpected challenges on using that at all?
So software took a bit of time to get really used to those and get it all up to speed. Hardware-wise, it was actually pretty simple. We have a square chassis with 2 H-bars in the middle, and we just kind of plug and play, bolted on, wired up. It's good to go.
Let's start to go through your cargo path. Alejandro's going to cover the hardware side of it. Then we'll cover some software for it as well too with Cooper. So talk to me about, of course, what's gone into it, any iterations you might have made throughout the season, and let's give it just a general overview of this really slick looking robot.
Yeah, all right, so let's start with the intake. So we took a priority in creating a rigid and compliant design with our new intake. We have 3 rollers running here, powered by a Falcon 500, moving at a 4:3 reduction, all belted together. We've gone through about 5 or 6 iterations, each more different and better than the last. And so we pass the cargo up through over the bumper and into our indexing system. Our indexing system uses 1 motor, a Falcon 500, and 2 rollers spinning in opposite directions, guiding up into our turret. So our turret this year has 180 degrees of travel. We're using 1 Falcon 500 for our flywheel, moving at a 1-to-1 ratio. And the flywheels are actually powered together. We have a 4-inch neoprene roller in the front here, and that's geared together here in the back to our 2-inch top roller. And those work together to reduce our backspin in our shots. This year we also included a continuously variable hood mechanism with about 24 degrees range of motion, and that's powered by a Neo 550.
Let's break this down a little bit on kind of each area. I want to ask a couple things. Just intake going into like your transfer area. I see some extra riveted on here. I've seen teams. One of the teams you talked about actually modifying their bumpers a little bit, but it looks like you've added grip here. So talk to me about was that something like added at a recent competition, or what was the impetus behind that?
We noticed a little bit of variance in our compression moving into the robot. So we added just black tread that like on normal drivetrains. And we noticed that they have a really good grip with the fuzz around the ball. And it's really important that they come over our swerve modules into that ball shelf that we call. And that leads straight into our indexer, no problems.
And then from your indexing type area, I know we'll be talking software in just a little bit for it, but from a hardware mechanical standpoint, the curve that you have on there, I noticed there's a little bit of extra kind of a grippiness on that. Can you talk to me about what kind of this area right in the middle is?
Yeah, so we have these 2 polycarbonate rails that basically guide the cargo up. Very lightweight. That was one of our key design moments here. So it's very simple design. These 2 redirect plates just funnel into it. We have very minimal gripping material to add a little bit of compression and control onto our balls.
And then from your turret perspective, we've seen teams either choose a lot of times to go with like a tank drive with a turret or maybe a swerve drive without a turret. Why was it important to Valor to have both a swerve and a turret this year?
We thought that the swerve and turret combination would be important later on when dealing with predictive shooting as well as dealing with defense. Being able to be at any orientation relative to your intake and shooting was deemed as a crucial design constraint.
Cooper, let's talk about some software from the ball path here. I'd love to hear about some of the sensors that you're using or any automation processes that go into it.
Yeah, so I can show you here really quick. The first thing to go through is our intake. And so one crucial design we made is that we gave space. Here, I'm going to go for it really quick. So one of our crucial design constraints was that we needed a good way to index our cargo as they're coming into the robot. So if you actually look down here, we have a banner sensor, I'm not sure if you can see it really well, that is going to track every ball that comes into our feeder, our indexing system. And then we also run a current sensing on our intake so that after we've intaked 2 balls, we can't actually continue to pick up extra cargo so we don't draw those penalties.
Yeah.
Next thing to go through, major design for the software on the turreting. Andrew, if you want to help me out. We have a limelight tracking on our shooter, so that here, one sec, I'll show you in a second. Basically, we have auto tracking on our shooter at all times during a match, and as we move further away from the target, which we'll simulate right now, you can see our hood and our flywheel speed will increase so that it's automatically tracking. We're always ready to shoot. And that was one of our major contributions in software to the shooter.
From on the field, I know you guys shoot all over, but where's kind of your sweet spot for Valor?
So we actually kind of have a sweet ring, if you want to call it.
Yeah.
We have a donut, basically between the anywhere in the tarmac or the backside of the tarmac all the way to the launch pad.
I've heard other teams call it the donut, by the way, too. I don't know if that's
Yeah.
become like a colloquial term amongst the first community or what's going on for that, so really cool. Let's talk about your climber as well, too, going into that. I'd love to hear about your climb sequence and showing off some of the design that's gone into that. So I think we're going to bring Andrew's going to come back in and talk more about your climber.
So our climber is effectively a 2-stage design. It has a center dynamic stage, as we call it, since it pivots out, and then we have 2 stationary static stages. The static stages both have a ratcheting hook on top, and the dynamic stage just has this fixed hook with extra grip tape in here to prevent swinging. When we reach out, we extend up. So Cooper, you want to show the sequence? So we extend up to roughly this height, grab them onto the main bar, bring it down, and then once we're on mid, to get to high, we use a software set point, so basically. So that now we would be touching high, and then we'd pull down, and these things would ratchet in, and now we do it all again to get to traversal. This is powered by 2 Falcon 500 motors, roughly a 6-to-1 reduction. It's a 1-stage gearbox, which is super compact, which is just a huge goal, as well as it's light. And those are 2 Falcon 500s, give us about 0.6 seconds of time to climb, or to go from all the way up to down, even loaded with the robot. Everything is pocketed using ISOGrid, which is it's a pretty good pocketing pattern used by aerospace companies. And then, you know, we looked at it and it was putting a lot of load on the back bar. So we added these tie rods that distribute the load out to the rest of the chassis, which just make it extremely stiff, and it's really tied in with the whole robot.
When you were analyzing the game as coming in, what was kind of like your mark of like how many seconds you wanted to climb in, and then where are you at right now in comparison to that?
So, you know, we thought, I think anything under 15 would have been pretty solid at the beginning.
Sure.
And we've gotten this design, you know, we never like run it to full until just a week ago. We've been running like 60% retraction power as well as waiting for it to swing. And that was yielding like 15 seconds like we thought we would. And now we recently put up all the way to full with all the software automation. We're able to get around a 7-second fully traversal climb from ground.
Well, as we're filming this in the end of day one, your team has 3 wins in your pocket already, so can't wait to see more of 6800 competing here. So, of course, good luck here at Texas Championship. I hope to see you at the World Championship as well. Thanks a lot for taking the time. Thanks to Kettering University for their support of this video. Did you know that over 30% of the student population at Kettering University was in high school robotics? These same students have received a portion of over $7 million in robotics scholarships from Kettering University. See why so many in first chose to go to Kettering University at kettering.edu. Don't forget to like, subscribe, and ring the bell to stay up to date on our new videos. Keep the conversation going and provide your input to our content. Watch our live shows at twitch.tv/firstupdatesnow. Join our Discord at discord.gg/firstupdatesnow and check out Fun FTC on Facebook, Instagram, and Twitter, and First Updates Now on Facebook, Instagram, TikTok, and Twitter.